Okay, good morning. Welcome to yet another exciting session on Introduction to Photonics. So, we have gone on to looking at the fundamental principles related to photon interaction with atoms. That is the exciting part, your exciting material with photons, right. And through that process we can actually learn about light generation and amplification. So, that is the learning objective that we have, and with that in mind, we started looking at an elementary atomic system consisting of two energy levels, wherein we were tracking three different processes. You could have absorption, and then with the absorption process you are taking an atom to an excited state. Essentially you are taking an electron from the valence orbital to one of the higher orbitals, and once it is at that higher orbital, we said it cannot stay there forever, it is going to have to come back to the original state, and it can come back by emitting a photon. And if it is emitting a photon after spending some characteristic lifetime there, we call it spontaneous emission. But we could also have an emission process which is triggered by an external photon that comes across this excited atom, and that process is what we call as stimulated emission, where we said we have, if you come in with h nu, one photon with h nu, and if h nu corresponds to the energy difference between the two energy levels that we are considering here, then we go out with a clone of the incoming photon, which essentially has the same phase, frequency, as well as direction, right, the same phase, frequency as well as direction you could get. So, you are essentially having a process that is known as amplification. So, essentially stimulated emission is a key process for amplification. So, then we started looking at this system under steady state conditions, what are the different rates of these processes, and then we came up with an expression for this emission probability density, which is an important factor that determines how much of the light is undergoing stimulated emission versus spontaneous emission. And then we got an expression like this, and then we said, okay, this is similar to, or Einstein actually realized that is similar to what Planck had derived for black body radiation, and through that we were going to we started getting into looking at what black body radiation meant. We started going back to looking at Boltzmann's law, and realizing that the probability of finding an atom at an excited state, EM, is always going to be lesser compared to probability of finding an atom at a lower energy level. So, we were essentially saying that the probability of finding an atom at an excited state is going to be lesser compared to finding an atom at a lower energy level. And then we went on to look at spontaneous emission a little more detail, and I was basically saying that spontaneous emission happens such that the higher energy level is depleted continuously, and so and that the depletion is actually an exponential. So, why is it an exponential? maybe we can expand on that a little bit. So, if you consider the number of atoms that are emitting simultaneously at any particular time t, let us say that fraction of atoms emitting is delta n2, okay. That certainly is going to depend on the number of atoms already at that higher energy level. So, it depends on having a certain number of atoms at the higher energy level, and then it is going to be emitted with a certain probability, right. So, the probability density that we have defined is PSP, and then that is happening over, let us say, a time period of delta t, right. So, this is actually over a discrete time interval, but if you actually look at the continuous emission, you basically say that dn2 over dt, you can write it as minus n2 PSP. Why am I putting minus there? Because it is decreasing, right. It is obviously when you are emitting these photons in a spontaneous manner, you are actually depleting that population in that excited state. So, this would essentially provide a solution which is given by n2 of t equals to n naught, or whatever was the population at time equal to 0. Maybe we can write it as n2 of 0, right. So, at time equal to 0, exponential of minus PSP multiplied by t, right. So, that is the solution you get for spontaneous emission, and that is what we are essentially representing over here, where PSP is what we have identified over here. PSP is equal to 1 over that spontaneous lifetime, okay, or rather that spontaneous lifetime corresponds to the time where that N2 population goes to 1 over E value of whatever it was at time equal to 0, right. So, this of course, we will also see, we will start looking at this other quantity wherein we say PSP for a given volume is going to be given by C over V multiplied by sigma of mu, okay, where sigma of mu, this is what we are going to use as we go on. We will not look specifically at the probability density every time. We will actually look at, we will refer to this sigma value, which is corresponding to what is called transition cross section, okay. So, we will, instead of representing in terms of probability, we will represent it in terms of what is called a transition cross section, okay. So, the transition cross section is typically expressed in terms of meter square or centimeter square, right, and clearly in this case the volume is in meter cube, and probability density is actually unitless. So, just to normalize, just to make sure that the units are agreeing, we or the probability density actually corresponds to the rate at which the spontaneous emission happens. So, to make sure that things are the dimensionally correct, we have that c, which is actually the corresponding to the speed of light, that is in meters per second. Okay. So, we will see that when we are quantifying a lot of these probabilities, we will start expressing that in terms of this sigma, which is called the transition cross section. If it is transition cross section corresponding to emission, we will call that sigma E. If it is transition cross section corresponding to absorption, we will call that sigma A. Okay. And but what we realize in this case is that both those cross sections are equal for the case that we have taken here, which is considering just 2 energy levels. But if you have multiple atoms, multiple energy levels, those transition cross section values can be different as well. We will look at that in a little more detail as we move on. So, beyond that, we went on to looking at, so we were defining what type of atomic systems that we are going to deal with. We said, okay, there are atomic systems which follow the Fermi-Dirac distribution, and there are atomic systems where under thermal equilibrium conditions, it actually corresponds to the Boltzmann distribution, but we will introduce another distribution here, which is also which is called the Bose-Einstein distribution, right. So, we will see that we could describe the emission statistics from these dilute gas of atoms in terms of Bose-Einstein distribution. So, from that perspective, the emission from these are known as bosons, whereas the emission from these are typically called as fermions. So, somebody had this question about photons as bosons the other day. The particles that satisfy Fermi-Dirac distribution are called fermions, and the particles that satisfy Bose-Einstein distribution are called bosons. Okay. So, we were looking at these 2 classes of systems from which light could be emitted, and then we came up with this expression for the thermal equilibrium condition, and we were starting to understand what this expression means, right. And the first case we were taking was when the thermal energy is greater than the energy difference between 2 energy levels. So, if you say your system has all these energy levels, let us say with energy difference of delta E, okay, if your thermal energy is such that it's greater than delta E, right. So, what that means is you are going to have a lot of electrons occupying the higher energy levels, right. So, but nevertheless what we will find is, because you have all these electrons that are so if the electrons are having that higher energy level, then the probability of emission is fairly high. So, that is what mathematically you will see also, right. So, this will correspond to probability of emission being very high. but nevertheless what we will find is that the spontaneous emission is more probable compared to stimulated emission, and this is the characteristic that we find with thermal light sources. Okay. So, what we were talking about at the end of last session was that this is the condition for incandescent light sources. So, you just heat up that material and to fairly high temperatures, so that you have a lot of electrons going to higher energy levels, and then you have a probability that these will emit photons, but nevertheless because of the fact that they are following the Boltzmann distribution. The Boltzmann distribution, what does it say? What does it say about N2 versus N1? So, N2 is always going to be less than N1, right, because the probability of occupying a higher energy level is lesser compared to the probability that you will find that electron at a lower energy level. So, N2 is less than N1 as far as thermal equilibrium conditions are concerned. So, because of that we will see that the spontaneous emission rate is more probable compared to the stimulated emission rate. And if we were to go into this a little more detail, what we will find is the probability of finding n photons emitted with energy h nu, right. So, we are basically talking about emission with energy h nu corresponding to the energy difference between the two energy levels, that we can call as P of n, right. But as far as spontaneous emission is concerned, each of those emission events is actually an independent event. Okay, one is not dependent on the other. So, you can the probability of emitting one photon would correspond to this value, and so probability of emitting n photons, since it is statistically independent, will correspond to that expression exponential of minus h nu over kBt, that would be to the power of n. However, since when you sum all these probabilities, probability of emitting 1 photon, 2 photon, 3 photon and all of that, if you sum for n equal to 0 to infinity, that has got to be equal to 1, right. Since that sum of all these probabilities will have to be equal to 1, you have essentially an expression for under this condition you have an expression for P of n, which can be derived as 1 over n bar plus 1, n bar over n bar plus 1 to the power of n. This actually was what originally S.C. Bose had derived, okay, and then it got that validated by Einstein. So, Einstein also supported that theory, and then so they came up with this. So this is actually what we call as Bose-Einstein distribution. Okay, and in such a case, so we are talking about thermal light sources, right? It's actually following this Bose-Einstein distribution, and it's where we can quantify n bar. So n bar is now going to be given by 1 over exponential of h nu over kBt minus 1, right. So in this, where n bar is given by this expression. Somebody has a question here. Yes. So what we are saying is, you are having a system with a limited number of atoms. It's consisting of a limited number of atoms, and they are all excited at with some thermal energy, right. So they are all going to the higher energy level, right, and from that higher energy level, that they will emit photons is actually a certainty. So what we are saying is, they will emit a photon, but then we are saying, what is the probability that you will find at any particular instant that n photons are emitted. So they may be emitted at different time scales. So they will be emitted is a certainty. That is what the summation is saying, but they will be emitted at different time scales, and they will be emitting at different number of photons also. So the probability of emission, the total emission has got to be equal to 1, but the individual probabilities you can define. Right, yeah. So if we actually plot this P of n, so you or rather we have had this discussion before, where we were looking at the probability of emitting n photons for a generic light source, right. And we were actually talking about, last week we were talking about that probability. If you have n bar equal to 10, it does not mean that you will exactly emit only 10 photons. There is a finite probability that you might actually be emitting only 5 photons, or there is a finite probability that you are emitting 0 photons within a particular interval, right. So we were looking at that picture for a generic light source that could be basically a laser type of light source, but now we are looking at thermal light sources, okay. And in thermal light sources, we are saying that we have this sort of distribution. So we were saying that generally with light sources, we follow the arrival statistics, follow a Poisson distribution, and that is where we were looking at P of n as a function of n. But now we are talking about a different type of light source, which is just thermally excited, okay. And for thermally excited light sources, if we look at P of n as a function of n, okay, P of n, let us say this corresponds to 1 and 0.1 and 0.01 and lower than that, and n corresponds to 0, say 5, 10, 15, 20 and all that. Okay. In this case, what we will find is that for n bar equal to 0.1, so let me just see what colors I used. So I used red, blue, green. So for 0.1, so this is basically n bar value of 0.1. If you plot this expression, is going to look like this. And then for n bar equal to 1, right, it will be like this. And then for n bar equal to 5, right, and so on. So if we go to n bar equal to 10, maybe something like this, and so on. So what do we see here? As far as your normal light sources are concerned, when I say normal light sources, I am talking about what you have in a laser, for example, the output of a laser. You have these statistics which say that, okay, there is a finite probability outside of that n bar value. So if you say 10 is my n bar here, the mean number of photons emitted is 10. So you will have a finite probability of finding 10 photons in any given interval, but that is the highest probability that you have. Okay. And then it is actually going down drastically beyond that, right. We were actually nitpicking and we are saying that probability of finding 0 photons in a given interval is actually a fairly small number, but it's still a finite number. We were saying that, right. But now look at this picture. What can we say about this picture? The distribution is much flatter. Okay. Which source would be more random? Which is more random here? This source is much more random than the other source. Okay. Because statistically, if you consider, for example, n bar equal to 10, there it actually goes to a maximum and falls off on either side of n equal to 10, right. But here it's just quite flat, which means that there is actually in this case what it's saying is that even though we have n bar equal to 10, there is actually a probability that you will find only 0 photons emitted within a particular time slot. Okay. That probability is actually even higher than finding 10 photons emitted. So it's like completely random sort of emission. Okay. So we were previously discussing this randomness in terms of a quantity. What were we discussing? How did we characterize this randomness? In terms of a particular phrase we were using. Coherence, right? We were talking about that statistical, the randomness of light emission we are characterizing in terms of coherence. So what we can say is thermal light sources are relatively incoherent compared to these other light sources, like in the case of a laser, for example. Okay. So thermal light sources, as in the case of sunlight or in the case of incandescent light, which are basically black body radiation, is fairly incoherent, fairly random light sources. This is what we were saying. So the key point is there's a broader distribution, or in another case more random emission is what we are talking about. So what we are saying is that emission, first of all, you cannot say at this point this many photons are getting emitted, right. So that actually is an uncertainty, but the specific question is, why is it that emitting 0 photons is more probable than emitting higher number of photons? And that is basically because when you look at the probability that we have here, we are saying number of photons, since they are statistically independent, the number of photons that you emit is going to be, if it's n number of photons, it's to the power of n. So it's actually statistically less probable that you will have that many photons emitted at the same time. Okay. The key thing is that we are looking at the number of photons that are emitted simultaneously or within a very small time scale. So what we are saying is, so the question is, are we implying that most of the time there is nothing emitted? That is not what we are saying. I mean, there is emission happening clearly, but the probability that within a particular time slot you find 0 photons emitted is more. When we are looking at in light emission from an incandescent lamp, there is continuous, I mean what we see sunlight, it's not like sunlight goes on and off, right. It's in a perceivable manner because we are time averaging all of our things. There's a lot of emission that's happening. However, you can take sunlight and you can maybe go to a nanosecond time interval, and there is a good chance that you will find 0 photons compared to chance of finding 1 photon, 2 photon and all of that. You will have to consider that this is the entire distribution we are talking about, and it's flat. In other words, if I were to draw this for n bar equal to 20, it will look even flatter. What does that tell you? And it's telling me that there is equal probability of finding 0 photons as there is finding 100 photons, right. That's what it's quite random is what we are saying. Okay. So it doesn't mean that no photons emitted at any particular time. You have photons emitted, but the probability of finding 0 photons is slightly higher, and then when you consider large number of photons, that is actually a flatter probability. So we are saying that the emission is just random. That's the key point. Right. Now what we are saying is, we are choosing a time interval, but assuming that all this propagation happens in sort of the statistics of propagations are not distorted. We can map what our observation is to the time of emission. So from that perspective I am talking about, right. But we are essentially looking at we are looking at it from an observation viewpoint typically. Okay. So that is one observation. Observation number 2 is the case where if you consider optical radiation, right, for optical radiation, h nu, what can we say about h nu? What sort of energies do we tend to see? For example, what is the energy for a photon with a wavelength of 1 micron? 1.24 electron volt, right. So it is in the order of an electron volt. So you can say this is in the order of electron volt. But what is the thermal energy? kBt is 25.6 milli electron volt at room temperature. Right. So what we see is h nu is far greater than kBt. If h nu is far greater than kBt, if h nu is far greater than kBt, what can we say about this emission probability density? So this is going to be a fairly large value. So then the emission probability density is going to be far less than 1, right. So and as a corollary, you can say that since emission probability density shows up here, right. So which is corresponding to the stimulated emission term, you can say that the spontaneous emission is going to be more probable than stimulated emission, right, if that emission probability is very low. So this is basically saying R spawn is far greater than R stim. Okay. So this is saying that for optical radiation you cannot get stimulated emission, or you have very low probability of getting stimulated emission unless what? All this expression has assumed one specific condition. What is that condition? So we said it's steady state, but then we said there's some other condition that we are considering. Thermal equilibrium conditions, right? So all this, so in this sort of a case, optical radiation is not possible, stimulated optical radiation is not possible under thermal equilibrium conditions. So that's what this is saying, right? So this implies that all sources that rely on stimulated emission, for example, as in the case of lasers, right, should operate well above thermal equilibrium. right. All sources that rely on stimulated emission should operate well above thermal equilibrium. And maybe we can look at this in a little more detail. Under thermal equilibrium, if we are looking at finding an atom at a excited state, right, it's going to be something like let's say like this at a temperature T1, right. If you go to a temperature T2 which is greater than T1, right, the probability is like this. Nevertheless, if you are looking at an probability of finding an atom at a higher energy level, even at T2 or even as you increase the temperature, you will find that probability is always lesser compared to finding something at a lower energy level, right. So, under thermal equilibrium conditions, you cannot have N2 greater than N1, right. So, that is what we are saying here. We cannot have N2 greater than N1. And so, if we need to make N2 greater than N1, you need to be well above this thermal equilibrium condition. Okay, you need to break free of this thermal equilibrium condition. So, essentially what am I talking about? We need to bring in some other energy into the equation. We cannot rely on thermal energy, because you just keep heating the material higher and higher, you will get more emission. That is what we see. You take an incandescent lamp and you give more and more current to it, you crank up the current, it becomes brighter and brighter, right. But it's still in thermal equilibrium condition, which means that as far as optical radiation is concerned, it is all only spontaneous emission that we are getting. Okay. So, that is our observation 3, right. So, if you want to get the stimulated emission rate to be greater than the spontaneous emission rate, you essentially need to have N2 greater than N1, right. So, you need to have essentially more number of atoms at an excited state compared to the lower energy level. And of course, beyond that you also need these photons coming in to stimulate the transition. So, that is another thing that we need, but basic condition you require is that N2 should be greater than N1, right. And this is a condition that we call as population inversion. Okay. And this is accomplished by external pumping or external excitation other than thermal excitation. So, what are we saying? We are saying that to get gain, optical gain, or in other words multiplication of photons in a medium, you need stimulated emission, right, and to get stimulated emission you need external excitation. So, if I am building an amplifier with some gain G, so what does that mean? I am coming in with some photons h nu, I am going out with lot of photons at that same frequency, say the same energy, right. And to achieve this, what I need now is some external pumping, and this external pumping can be in terms of optical radiation, right. So, you can come in with optical radiation to excite to a higher energy level, right, and from there you could have stimulated emission, or you could have electrical means of pumping, right. You as in the case of semiconductors, what we have is we by electrical injection of carriers, you can have a lot of electrons in the conduction band and holes in the valence band, and then you could have recombination of these electrons with the holes, which result in optical radiation. Okay. So, you could in that case it is actually electrical energy that you are putting in, but here in the other case you can think of it as optical energy. Okay. So, you need some external energy source to get over this thermal equilibrium condition and have this stimulated emission possible. Okay. And that actually takes us into this exciting topic of optical amplification, which we will look into more detail in the following lectures. Okay. So, let me stop at this point and we will continue next lecture.